Welcome to lecture 25, orthonormal bases and the Gram-Schmidt method. So we're going to take a look at some spanning basis sets. Suppose we have a set of four tuple vectors. U1 is 1, 1, 1, 1. U2 is 1, minus 1, 1, minus 1. U3 is 1, 2, 3, 4. And U4 is 1, 0, 2, 0. How do we tell whether these vectors span R to the fourth? Now remember, spanning means that any vector in R to the fourth can be written as an expansion with real coefficients of U1, U2, U3, and U4, and that expansion is unique. So if they form a basis, then any vector V1, V2, V3, V4, those are the components in the Cartesian basis, can be expressed as the sum over the four basis vectors U1, U2, U3, and U4 via the following. V is equal to C1U1 plus C2U2 plus C3U3 plus C4U4, and we have to find out what these coefficients C are. We can write this as a matrix problem. MC equals V, where M is this matrix that's written for you here. And you should be able to verify directly that this equation is the equation I need to solve in order to find whether or not an arbitrary vector V can be expressed in terms of these basis vectors U1 through U4. Well, this is a row reduction problem now. We know when row reduction problems can be solved. It's when the determinant of M is non-zero, then they can be solved. So we form a matrix out of the columns given by the basis vectors, and if the determinant is non-zero, then those basis vectors will span the vector space. That's all there is to it. We have to have enough basis vectors equal to the dimension of the vector space, but as long as we have that, then this is the criterion to determine whether or not a set of vectors will span the vector space. So let's find the determinant. We're going to expand by minors on the fourth column because there are two zeros there. And so determinant of M is minus 1. That's the first element times the determinant of the 3 by 3 matrix I get by crossing out those two, that row and column, plus minus 1 times 2 times the determinant of the matrix formed by crossing out the third row and the last column. And now I work out those 3 by 3 determinants. I find it's equal to minus 4 plus 8, which equals 4. Key point is that's not 0. And so these vectors do span R to the fourth, and they can be used as valid basis vectors for R to the fourth. So the solution can be found, and these vectors do span R4, and since there are 4 of them, they form a basis as well. All right, so in general, we would rather work with orthonormal basis sets. The basis discussed on the previous slide is not orthonormal. So U1.U2 is, or UI.UJ is not equal to 0 for every I in J, and every I not equal to J. And it's much easier to find the coordinates when you have an orthonormal basis. So one such orthonormal basis for Rn is the Cartesian basis, 1, 0, 0, 0, 1, 0, 0, etc., 0, 0, 1, 0, etc., all the way out to 0, 0, blah, 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 up to 1, with just a 1 in the last element, or the nth element. Now it's very easy to see that ei.ej in this basis is equal to 0, except when I is equal to j when it's equal to 1. So this is an orthonormal basis. Because I have n basis vectors and the dimension of my space is n, they obviously have to span, and so they are an orthonormal basis for R to the n, and in fact that's the basis that you're most used to working with, this Cartesian basis. So there's another similar basis that is less well known, and I want to introduce it to you, and it starts with the first basis vector being the set of all 1s divided by 1 over square root of n in order to make it orthonormal. And then I have to construct n minus 1 vectors that are perpendicular to that. So n perpendicular to each other. And so the way I do that is I do 1 minus 1, normalize it. I do 1, 1 minus 2, normalize it. 1, 1, 1 minus 3, normalize it. 1, 1, 1, 1 minus 4, normalize it. All the way out to n minus 1 1s. That should be, I guess, a minus n minus 1. And then I think the normalization might not be quite correct. And then those can easily be shown to be orthonormal. And since there are a total of n vectors, they also span the space. So slight error on that last one. It should be minus n minus 1 minus the quantity n minus 1. And then I have n minus 1 plus the quantity n minus 1 squared. That becomes n squared minus 2n plus 1. I think it becomes n squared minus n is the denominator that is the thing that we would renormalize by. But the point is that there are n of them, so they have to span the space. So now, a question is there a direct way to construct an orthonormal basis if I'm given a set of vectors? And the answer, surprisingly, is yes. This method is called the Gram-Schmidt Orthogonalization method, and we're going to do this by constructing the unit vectors one at a time and removing the projection onto all of the current unit vectors to extract the next unit vector in the series, and then we normalize everything that's left over so that we have a orthonormal set of unit vectors. And it's best to see how this works by direct construction because it's not that easy to write down the equations and really understand it. You actually have to go through the algebra and really construct it. So let's show how the Gram-Schmidt orthogonalization method works. Suppose we start with a set of basis vectors v1 out to vn. What we do is we set e1 equals v1 divided by the norm of v1, obviously a unit vector. We make e2 v2 minus the projection of v2 onto e1 times e1. So I subtract off the part of the vector v2 that can be represented or is proportional to v1, and then I normalize the whole thing. The third one would be v3 minus the projection of v3 on e1 minus the projection of v3 on e2, and then the whole thing normalized. And then you do the same thing on and on again. So e4 would be v4 minus the projection of v4 on e1, and then minus the projection of v4 on e2, and then minus the projection of v4 on e3, and so forth. And then once I've removed all of those projections, we then normalize the final result. And each time we subtract the projections onto all of the current basis vectors, and then we normalize at the end to make a unit vector. All right, let's see an example of how this works. We're going to go back to our old set that we were working with before, U1, U2, U3, and U4. These are the ones that we were working with before. So the procedure is we take U1 and divide it by the norm of U1. Well, the norm of U1 is 2, and so it's 1 over 2 times the vector U1. For E2, I start with U2 and I subtract the projection of U2 onto E1, but U2 dot E1 is equal to 0. So I just take the vector U2 and normalize it, and that's given for you there. Now for E3, I have to subtract off the projection on U1 and the projection on U2. Now that projection on U1, when I work that out, I'm going to find that it's 1 minus 5 halves. So how do I get that? Well, I get 1 plus 2 plus 3 plus 4. Okay, 1 plus 2 plus 3 plus 4 is 10. I have to divide that by 2 because I'm taking the dot product with E1, so I get 5. That's E1 dot U3. But then I have to multiply it by E1. Well, E1 is 1 half times 1, 1, 1, 1, 1, so I get this 5 divided by 2, and I have to subtract it. Now for the next one, when I look at the dot product between U2 and U3, or E2 and U3, I'm going to get 1 minus 2 plus 3 minus 4. That's a net of minus 2. I have to divide it by 2 because that's how I get E2 to be a unit vector, so it's minus 1. And then I multiply it by the unit vector, which is 1 half times 1 minus 1, 1 minus 1. And now we have to do the subtraction. So let's look at each component. I have 1 minus 5 halves plus a half, so that's 1 minus 2 or minus 1. I get 2 minus 5 halves minus 1 half, so that's 2 minus 3, that's minus 1. I have 3 minus 5 halves plus a half, so that's 3 minus 2 or 1. And I have 4 minus 5 halves minus a half, so that's 4 minus 3 or 1. And now let's normalize that. The normalization of minus 1, 1, 1 is going to be 1 over 2. Okay, and now we go for our last one, E4. I take 1, 0, 2, 0. I have to subtract off the projection on E1, the projection on E2, and the projection on E3. So the projection on E2, E1 dot U4 is equal to 3/2. E2 dot U4 is equal to 3/2. And E3 dot U4 is equal to -1/2. And so now I have to go through this algebra. I'm not going to say it for you. You can sit down, pause the video, and carefully go through this algebra and get your result. And when all the dust settles, you find it's equal to -1/4, 1/4, 1/4, -1/4. We have to normalize that, so we get 1/2 times -1, 1, 1, -1. Now take a look at these four vectors. I have 1, 1, 1, 1. I have 1, -1, 1, -1. I have -1, -1, 1, 1. And I have -1, 1, 1, -1. You can see that there's a pattern that has developed here this is yet another set of orthonormal basis vectors that are fairly easy to construct. This set I think you can only make in Rn, where n is a power of 2. So I can do it for R2, for R4, for R8, for R16, and so forth, but I can't do it for R3, and I can't do it for R17, and so forth. Okay, that's all that we have on this. You're going to get a chance to practice doing Gram-Schmidt orthogonalization with the in-class problems.